Good afternoon, students. Today we are going to see new chapter P block elements 2. So before that, let's see how many chapters are over so far. So we have completed for June month. If you see here in our index page, we have metallurgy first, followed by P block elements, and then we had solid state. So all these three chapters we have completed. Next we are moving on to the next month chapter, that is July month chapter, that is P block elements 2. So next we have to start with P block elements 2. So we have 7 chapters in volume 1. Of 7 lessons we have completed 3, that is chapter 1, 2 and 6 we have completed. Now we are going to start chapter 3, that is P block elements 2. So as I told already in P block elements 1 chapter, this P block elements, it is having two divisions in our textbook. So in the first in the first part we would have discussed about group 13 and 14 alone. Here we are going to discuss 15, 16, 17, 18. Remaining 4 groups we are going to discuss in P block elements 2. So let us start with this P block elements 2. So this lesson, it is quite bigger. So out of the 7 chapters in volume 1, this P block elements 2, it is very vast because we are going to discuss 4 different groups. Whereas in the second lesson we would have discussed only 2 groups, that is 2 families. Here we are going to discuss the group 15, 16, 17 and 18. So the lesson is going to be little bigger. We have to follow regularly. Clear? So same way we will be seeing the preparation properties of nitrogen and phosphorus, followed by oxygen and sulfur, and the halogen halides and interhalogen compounds, and then followed by the noble gases, and what are the importance of these P block elements in our daily life we will discuss. So first we'll see, we have already learned the general characteristics of P block elements of the first 2 groups, namely icosagens, that is boron group, and tetragens, which is the carbon group. So all these are objectives in the previous unit. Okay, so in this unit we will learn the remaining P block groups: pnictogens, chalcogens, halogens and inert gases. So pnictogen is group 15 nitrogen family, chalcogen is oxygen family, halogen and then inert gases or noble gases. So first, today we are going to see group 50 nitrogen elements. Nitrogen and ammonia alone we are going to discuss today. So group 15 element, group 15 is nitrogen group. So oxygen about 78 occurrence about 78% of the earth atmosphere contains dinitrogen gas. So if you see the atmospheric presence of nitrogen, it is 78%, it is present in atmosphere. It is also present in earth crust as sodium nitrate, which is chill saltpeter. So we have to remember this alternative name also. What is the other name for sodium nitrate? It is chill saltpeter, and potassium nitrate, Indian saltpeter. The 11th most abundant element, phosphorus, exists as phosphate, as fluorapatite, chloropatite and hydroxyapatite. So the other elements like arsenic, antimony and bismuth are present as sulfides, and they are not very abundant. And moving on to the physical properties, their physical state, they are all solids except nitrogen at 293 Kelvin. Their atomic number is given. They also form isotopes, and atomic masses, they are all increasing, and the electronic configuration is inert gas configuration they have given, and then atomic radius, it is again increasing, density is increasing, melting point, only the arsenic, it sublimes, melting point and boiling point, it sublimes. What is meant by sublimation? Directly converting from solid to gaseous state. So arsenic has the property to sublime at 889 Kelvin. Moving on to the preparation. So we will be seeing the preparation properties and uses of the nitrogen. So nitrogen preparation. So nitrogen, the principal gas of atmosphere, because it is present 78% by volume. It is separated industrially from liquid air by the fractional distillation. So how it is separated from the atmosphere? By doing fractional distillation. A pure nitrogen gas can be obtained by the thermal decomposition of sodium azide. So sodium azide means sodium is Na, azide means nitrogen, 3 times of nitrogen, we call it as azide at 575 Kelvin. So what it will do, it get decomposed to give sodium and nitrogen separately. It can also be obtained by oxidizing ammonia using bromine water. So using bromine water, that is bromine gas dissolved in water is bromine water, by it is an oxidizing agent. So oxidizing ammonia, we will get the sodium, ammonium bromide and nitrogen gas. What are the properties? It is rather inert, and terrestrial nitrogen contains 14.5 and 0.4 of nitrogen, 14 and 15 respectively. So their isotopes are present. So nitrogen 14 is present in 14.5% and nitrogen 15 is present in 0.4% in the atmosphere. This terrestrial means in the land. Because the nitrogen, it is also present on the earth. Because of the nitrogen fixation for the plant survival, the nitrogen gas is very important. Then the later is used as an isotopic labeling. So nitrogen 15 is used for isotopic labeling. The chemically inert character of nitrogen is largely due to high bonding energy of molecules, that is 225 calories per mole. Interestingly, the triply bonded species is notable for its less reactivity in comparison with the other isoelectronic triply bonded systems. So if you see, we have N triple bond N, that is nitrogen. Other than that, we can see C triple bond C, C triple bond O, and cyanides, isocyanides, alkynes, all these are triply bonded. So all these are quite reactive, but this N triple bond N is less reactive than the other triply bonded atoms. So these groups can act as a donor, as a whereas dinitrogen cannot. So this dinitrogen will not act as an electron donor, whereas the other triply bonded molecules can act as a donor. However, it can form complex with metal and like CO to less extent. The only reaction of nitrogen at room temperature is with lithium forming lithium nitride with the other elements, and nitrogen combines only at elevated temperature, and group 2 metals like and thorium, they form nitrides, ionic nitrides. So generally it reacts with nitrogen to form nitrides. Direct reaction with hydrogen gives ammonia. So when you react directly ammonia and nitrogen and hydrogen, you will get ammonia, and this reaction is favored by high pressures and at optimum temperature in the presence of ion crystals. This reaction is the basis for the Haber's process. So you know very well what is Haber's process. Haber's process is the manufacturing of ammonia. We say the Haber's process, and this reaction is the basis of Haber's process. With oxygen, nitrogen produces nitrous oxide at high temperature, even at 3473 Kelvin. Nitrous oxide yields only 4.4% of nitrous oxide. What are the uses? Nitrogen is used for the manufacture of ammonia, nitric acid and calcium cyanamide, and liquid nitrogen is used for producing low temperature required in cryosurgery. So liquid nitrogen, it is very commonly used in cryosurgery and also used in biological preservations. Next is ammonia. Moving on to our next compound of this group 15, it is ammonia. Ammonia is prepared or it is formed by the hydrolysis of urea. So NH2CO, NH2 is urea that reacts with water to give to NH3 plus CO2. And ammonia is prepared in the laboratory by heating an ammonium salt with a base. And ammonia reacts with a base to give ammonia. Ammonium reacts with base, that is NH4 is ammonium that reacts with the base to give ammonia, and ammonium chloride again reacts with calcium oxide which is a base to give ammonia. It can also be prepared by heating a metal nitride like magnesium nitride with water. So metal nitride is any metal. Here we have taken magnesium nitride with water. It gives magnesium hydroxide and ammonia. It is industrially manufactured by passing nitrogen and hydrogen over iron catalyst. and that is at 750 Kelvin. So what is an ion catalyst? Is a small amount of potassium oxide and alumina is also used to increase the rate to attain the equilibrium at 750 Kelvin at 200 atmospheric pressure. In the actual process, the hydrogen required is obtained from water gas and nitrogen from fractional distillation of liquid air, and the properties are given. Ammonia is a pungent smelling gas and is lighter than air. It can readily liquefied by about 9 atmospheric pressure. So the liquid boils at minus 38.4 degrees Celsius and it freezes at minus 77 degrees Celsius. Liquid ammonia resembles water in its physical properties. So if you see, it resembles like a water, but you can have a smell is different. It is having a strong pungent smell, and it is also lighter than air. That is, it is highly associated through strong hydrogen bonding. So that is why they say they resemble water in physical property. So ammonia is extremely soluble in water, 702 volume in 1 volume of water at 20 degrees Celsius and 760 mercury meter pressure. At low temperatures, two soluble hydrate, it is ammonium hydrate, diammonium hydrate, they are isolated. In these molecules, ammonia and water are linked by hydrogen bond. So these ammonia hydrate and diammonium hydrate, they are linked by the hydrogen bond. In aqueous solution also, ammonium may be hydrated in a similar manner, and we call it as an ammonium hydrate. And the dielectric constant, that is how much electricity it can store, we call it as a dielectric constant of ammonia, is considerably high to make a fairly good ionizing solvent like water. So it is given how beautifully it is getting ionized into ammonium and NH2, and water also again it ionizes to hydronium ion and hydroxide ion. So it is comparatively high than water because it is 10 power minus 30 for ammonia, whereas for water is 10 power minus 14, the dielectric constant. Their chemical properties, first is action of heat. Above 500 degrees Celsius, ammonia decomposes into its elements. The decomposition may be accelerated by metallic catalysts like nickel and iron. Almost complete dissociation occurs on the continuous sparking. So here at greater than 500 Kelvin, complete decomposition will take place into ammonium and hydrogen. Reaction with oxygen and air, it does not burn in air but burns freely in free oxygen. So if you see, air is a mixture of gas, this ammonia will not burn in air, whereas in a free oxygen it burns completely with the yellowish flame to give nitrogen and steam. In the presence of catalysts like platinum, it burns to produce nitric oxide. This process is used for the manufacturing of nitric acid, that is known as Oswald's process, very important. We will see again in the nitric acid. Next is reducing property. Ammonia reacts or acts as a reducing agent. Ammonia acts as a reducing agent. It reduces the metal oxide to metal. So what it will do? Ammonia, it acts as a reducing agent. We all know what is a reducing agent. It supplies hydrogen. Yes or no? So it reduces the metal oxide to metal, or removal of oxygen also we will say as a reducing agent when passed over the high metallic oxide. So here if you see, lead oxide is taken, PbO is lead oxide, with ammonia it gives lead and ammonia and water. So here lead oxide, from lead oxide we have removed oxygen. So removal of oxygen is an what? Reduction. So what helps for the reducing this lead oxide into lead? Ammonia has helped in this process. So ammonia can also act as a reducing agent. And reaction with acids, when treated with acid it forms ammonium salt. So what it will do, when we treat them with acid it forms ammonium salt, and this reaction shows that the affinity of ammonia for proton is greater than that of water. So since it is treated with acid, it is forming ammonium salt. Their reaction with proton, ammonia for proton, which means with acid, what does acid produces? It produces H plus ions. So that protons, they are highly fond of ammonia. So instead of dissolving in water, they have greater affinity to react with the acid, which is a proton. And reaction with chlorine and chlorides. Ammonia reacts with chlorine and chloride to give ammonium chloride as a final product. So it reacts with chlorine and chlorides, that is to give ammonium chloride as a final product, and the different reactions under different conditions you can see here. With excess of ammonia, this could be asked in 3 mark. With excess of ammonia, chlorine reacts to form nitrogen and hydrogen chloride, and with excess of hydrochloric acid and ammonia, you can see ammonium chloride is formed. With excess of chlorine, if you see, ammonia reacts to give nitrogen trichloride, which is an explosive substance. So when you see the reaction with the excess of chlorine, it gives hydrogen chloride and nitrogen trichloride, which is an explosive substance, and ammonium chloride is also formed. With excess of ammonia and with excess of chlorine, they may ask you in the complete the reaction or explain the reaction with the excess of chlorine and excess of ammonia and chlorine, they may ask chlorine and chlorides. And formation of amides and nitrites. So what are amides? So how the amides are formed? With strong electropositive metals like sodium, ammonia, they form amides, while it forms nitrites with metals like magnesium. So sodium reacts with ammonia to form sodamide, and magnesium reacts with magnesium to form magnesium nitride. So it forms sodium and ammonia, they form amide. When nitrites, they are with metals like magnesium, they form nitrites, which is because of the strong electropositive metals, they react with this to form amides and nitrites. With the metallic salt, so ammonia reacts with metallic salt to give metal hydroxides, that is, or forming complexes in case of copper, metal hydroxides in the case of iron. So iron 3+ state reacts with ammonium in the presence of a base to form an iron hydroxide, whereas copper 2+ reacts with ammonium to give a complex, which is a tetramine copper 2 sulfate, which is a complex coordination complex. And formation of amines. So ammonia forms ammonated compounds by iron dipole attraction. So it forms ammonated by having a dipole attraction. So can you see here? So calcium chloride is having a dipole attraction with ammonia to form ammonated compound. In this, the negative end of ammonia dipole is attracted to the calcium 2+ ion. So where do the positive and negative attraction taking place? Calcium 2+, it is attracting towards the negative end of the ammonia. It can also act as a ligand to form a coordination compounds like tetramine, cobalt, and diamine, silver. For example, when excess of ammonia is added to aqueous solution, copper sulfate, a deep blue color compound, that is formed. And finally, moving on to the structure of ammonia, 3-mark question, very important. Ammonia molecule is pyramidal in shape. So what is the shape of ammonia? It is pyramidal in shape. So NH bond distance, can you see here? It is 1.016 angstrom, and HH bond distance is 1.645 angstrom, and the bond angle is 107 degree. So the structure of ammonia may be regarded as tetrahedral with one lone pair of electron in the tetrahedral position. Hence it has a pyramidal shape. So if you can see here, it is having a shape, having a triangle, exactly not a triangle, but it is looking like a pyramidal in shape. On the top of a pyramid, you can see an nitrogen molecule. Over the nitrogen, you can see one lone pair of electron, which is surrounded by 3 hydrogen. So the what is this? Hybridization of this nitrogen is sp3. So how do you calculate the hybridization? Here you are having 3 sigma bonds, NH sigma bond along with 1 lone pair. So 1 s and 3 p orbitals join together to form an sp3 hybridization. So this is the structure of ammonia. So these bond angles they may ask, and what is the hybridization of ammonia in nitrogen in ammonia molecule, they may ask. Draw the structure of ammonia, they may ask in 2 mark, or these are the possible question from this part. So with this we'll stop here. In the next class we'll see about the nitric acid. So what are the preparation properties and uses of nitric acid, we'll discuss in the next class. So kindly do your assignment, please be regular, and this lesson is important. So please follow the classes regularly, finish your assignment and submit on time. Thank you.